Me llamo Narihiro Nakamura. Sorry, actually, I can speak Spanish, so I'd like to talk in English. But actually, my English is also not good. I do my best. Please bear with me. My name is Narihiro Nakamura. Please call me Nari. Today, I'd like to talk about Parallel Wars CBZC. But first, I want to say Argentina is great. All foods, thank you. All foods are very delicious, and Luis in Argentina are friendly and kind to me. And I played soccer with Luis in Argentina 2 days ago. It was really fun, but my muscles are sore. It's soccer's effect. When I play soccer, I felt we are Luis. We don't care about different country and different culture and different language. We are Luis. It's a great community, I think. I'm not from Argentina. I come to here from under. This means I'm from Japan. Japan is under from Argentina. Digging a hole is the shortest way, but I can't do it. So I took roundabout routes to Argentina. Anyway, Japan is the most far away place from here. So I think you may not know me. So I'd like to introduce myself with timeline. Before 2005, I was not a programmer. I worked at the ice cream factory. I worked in an assembly line. For example, I made many cardboard boxes. I was a professional cardboard box maker. So I made 150 boxes per hour. So I was like a machine. I went to computer school from 2005. I learned the Java language over 6 months. And I worked at the computer company since 2006. I used Java then. I worked in a big company. This work was similar to assembly line work. I made part of the product. I didn't understand the whole product. I was still like a machine. Then I met Ruby. I've used Ruby in my hobby. I changed job. My new company works using Ruby. I've been using Ruby in my work. Currently, I work at NSCL. NSCL is not short. NSCL is a company name. And Mats is my coworker. Do you know Mats? Yeah. Great. And Shugo Maeda is my boss. They are CRuby committers. When I started Ruby programming, I felt free. In Ruby's works, wasn't similar to assembly line work. I could make the whole product, so I was no longer a machine. Then I met garbage collection. This technology is very interesting for me. This is a garbage collecting machine. So I've been creating it since then. It's very fun. So I'm making a machine. Okay, I'd like to talk about my relationship to DC. I'm a CRuby committer, and I work on DC. And I wrote a book about DC, but it's only in Japanese, sorry. And I've been creating DC with RDD. What is RDD? RDD is RubyConf driven development. Do you know RubyConf? Yeah. RubyConf is the most popular conference for Japanese Rubies. Okay, let me talk about my RDD history. I created Lazy Sweep DC at RubyConf 2008 and 2010. Traditional mark and sweep DC executes mark and sweep atomically. Ruby application stops during DC. This is called stop the world. In lazy sweeping, sweeping is lazy. Each invocation of the object allocation sweeps Ruby's heap until it finds an appropriate free object. This improves the response time of DC, i.e. the worst case time of DC decreases. You can use lazy sweep since Ruby 193. But I omitted details of lazy sweep DC because it's not a main topic in my presentation. And I created parallel marking DC at RubyConf 2011. And it's the main topic in my presentation. Okay. Now, I'd like to introduce today's topics. First, why do we need parallel marking? And what to consider, and how to implement, and how much did performance improve? First topic is, why do we need parallel marking? This is CRuby's current DC. This means this operates on only one core. In multi-core environment, other cores don't help DC. So this is alone. We should run DC in parallel. Okay. First, let me explain a few DC-related concepts. What is DC? DC collects all data objects. What is a data object? A data object is an object that is never referenced by the program. In DC terms, we say that data object is unreachable from roots. Roots is a set of pointers that directory reference objects in the program. For example, Ruby's local variables and Ruby's global variables. For example, we execute this Ruby program in this case, string B is unreachable from roots. So it's a dead object. Please remember that this corrects objects that are unreachable from roots. Next, let me explain the current CRuby DC algorithm. CRuby adopts the mark and sweep algorithm. Corrector works in separate mark and sweep phases. In the mark phase, corrector marks live objects that are reachable from roots. For example, we execute this example program, A equals new array, and then we push new array to A and push string A to new array. And push string B to A. Finally, we pop string B from A. So this is the object relationship that is created by the example program. Please note that the difference from array A to string B is cut here. Then we execute DC start. In mark phase, all reachable objects from roots are marked. So string B isn't marked because string B is unreachable from roots. Ruby heap is divided into blocks. These blocks are called Ruby heap blocks. And Ruby heap blocks are divided into objects. After marking, all objects are categorized as dead objects or live objects. Here, black object signifies marked object. Gray object signifies unmarked object. In the sweep phase, corrector sweeps dead object. Dead means unmarked. Dead means unreachable from roots. In the sweep phase, corrector scans the entire Ruby heap. Corrector unmarks object if it's marked. And corrector sweeps object if it's not marked. In this case, string B is swept. After sweeping, this is completed. Okay. Now, let me explain the characteristics of CRuby DC. First characteristics is the stop-the-world algorithm. Next is single-thread execution. Today, I'd like to talk about single-thread execution. Recently, PC has multiple processors, but this executes on a single thread. Other cores don't work during DC. It's a waste. How can we fix this? How? So use parallel marking. What is parallel marking? Corrector runs several marking processes in parallel by using native threads. We will be happy on multi-core machine. This shows a flow diagram for parallel marking. The line at top of this diagram is the Ruby application execution flow. Following lines this execution flow. After the Ruby application is stopped, this is invoked. And this executes in parallel by using native threads. In this diagram, DC has 3 marking threads. Okay, next topic is what to consider when implementing parallel marking. We should consider 2 problems. First problem is the workload balancing. How can we divide the marking tasks into subtasks? I try to think about a simple approach. One branch of root is marked by 1 thread. A branch means an object which is referenced from root and its children. A branch and B branch are shown here. Usually there will be many branches, but only 2 are shown here. A branch is marked by A thread, and B branch is marked by B thread. So this means marking of single branch is performed by a single mark thread. Tasks are distributed to multiple threads. The task of marking the entire heap is divided into several tasks, each marking a single branch. This seems to be no problem, but actually this solution suffers from the workload problem. This illustration shows each mark thread has a branch. Each thread doesn't know what the other threads are doing. For instance, if A and B finishes work early, so then they will be stopped doing anything. I think machines should work forever. I think A and B should steal another thread's task. Let me introduce parallel marking with task stealing. If A and B finishes work early, day 3, this is called task stealing. Next problem is wait-free algorithm. What does wait-free mean? A wait-free program does non-blocking execution. It guarantees path-thread progress. Why is the wait-free important? Amdazo gives an answer for this question. Amdazo is used to find the maximum expected improvement to an overall system when only part of the system is improved. Amdazo is used in parallel computing. If parallel portion of the system is X% and number of processes is Y, how much speed up can we expect? This graph shows the overall speed up of the system. X-axis is a number of processors. Y-axis is a speed up of system. For example, if number of processors is 8 and parallel portion in the system is 95%, then execution is 6 times faster than with 1 core and 0% parallelization. But if parallel portion is 90%, then non-parallel portion is 10%. So this system can be speed up by a maximum of the factor of 10. no matter how many processors you use. So if you have any sequential parts, then they may be a bottleneck multi-core processors. It's worse than expected. The conclusion so far, we should consider how we can efficiently balance its workloads. So we use task stealing. And we should eliminate non-parallel parts by using weight-free algorithm. So next topic is how to implement parallel marking. In task stealing, threads steal tasks from each other. Task stealing is achieved with ORASDEC. DEC stands for the double-ended queue. In ORASDEC, the DEC contains tasks as elements. It's a weight-free data structure. ORASDEC has only 3 operations. First operation is pop. Pop operation removes the bottom task from DEC and returns it. It's same Ruby's pop method behavior, you know. Second operation is push. Push operation append the task onto the bottom of this DEC. Third operation is shift. Shift operation returns the first task of DEC and removes it. This shows mark worker 1 and 2 and 3. Each mark worker corresponds to a single mark thread. Each mark worker has single DEC like this. So only the owner worker can call pop and push operation. And workers can call shift to steal from other workers' DEC. In this case, worker 1's DEC is empty. So worker 1 calls shift operation of worker 2's DEC. Then worker 1 gets the task of worker 2's DEC. This is task stealing. Perhaps you think, doesn't shift operation have contention problems? In what ways could shift operation cause contention problems? Merge set may cause shift operation of same DEC at the same time. And shift and pop operation could be called at the same time when DEC has only one element. But Aurora's DEC avoids these contention problems. Shift is serious by using CAS, compare and swap. And this serialization doesn't use a log. It's a weight-free. But I omit details of the implementation of the serialization. For the sake of this presentation, let's assume that Aurora's DEC avoids contention problems. Okay, I'd like to summarize what I have said about Aurora's DEC. A simple data structure for task stealing. And each worker has a single DEC. And stealing is weight-free. How to use Aurora's DEC in parallel marking? How? First try, a task is an object. Let's say that worker A has branch that is composed of 4 objects. We start by marking A and pushing it to the deck. And then we pop A from deck and mark B and C. B and C objects are S children. Then we push B and C to deck. Then we pop C from deck, and we mark D and push D to deck. Finally, we pop D and B. This is branch marking. And next, how do you steal? Suppose that worker 1 has task B and C. Worker 2 has no tasks. Worker 2 steals tasks B on worker 1 by using shift operation. Let me summarize. Marker uses Aurora's deck as marking stack. A task means an object. The granularity of the task is very fine. This is a naive implementation. I implemented this approach, but it's slower than original DC. So I don't know. I fell into the pitfalls of parallel processing. I thought, why is it slow? Why? Pop and push and shift operations are called frequently because deck has fine-grained tasks. Their overhead is too big. How to fix this? We can make the tasks less fine-grained. A task is a branch. Now, all branches in roots are divided roughly among the decks. Worker A has branches on deck like this. Worker B has branches too. So now the deck holds only the top of node of each branch. And each worker traverses the rest of the branch without using the deck. When the deck is empty, the worker steals a branch from another worker. In this case, A's deck is empty, so A steals a branch on B's deck, like this. This approach has good point and bad point. Good point is number of calls to decks operations was reduced. So marking speed of the worker is improved. However, coarse-grained tasks decreases parallelism. Why do coarse-grained tasks decreases parallelism? Tasks may involve a large branch. If an object is B's branch has many child objects, then A can steal it while B is marking the large branch. So A must wait for B. Therefore, parallelism is decreased. So the worker needs to treat large branches as special cases. Almost all large branches hold large array objects and large hash objects. Actually, Each marker has a special deck to manage them. A marker divides them into fixed-size tasks. For example, first 10 elements of the array, next 10 elements of the array, and so on. By doing this, other workers can still divide tasks. This improves parallelism. Okay, I'd like to summarize what I have said about task-taking implementation. The naive implementation was slow because grain of the task was too fine. I changed the task to mean a branch in roots, so the grain of the task become coarse. It's faster. Okay. Next topic is how much did performance improve? There are my machine specs. My machine has only 2 cores. Parallel marking uses 4 marking threads. First benchmark program is make benchmark. This is a benchmark which used in CRuby development. So this shows the result of make benchmark. This shows the rate of increase in the performance when using parallel ZC compared to the original ZC version. Each line is the result of a single benchmark. If the line points upwards, it means that performance is increased. But if the line points downwards, it means that performance decreased. Next benchmark program is make RDoc. Make RDoc generate the Ruby documentation. This benchmark measures execution time and this execution time of make RDoc. It takes about 80 seconds on my machine. In fact, 30% of that time is spent on ZC. So how much did performance improve? Original DC takes 26 seconds, but parallel DC takes 16 seconds. It's 10 seconds faster than original DC. All DC time is improved by 40%. Thank you. In many core environment, I expect we get large improvement. But my machine has just 2 cores. I can see it. I explained the best case for parallel ZC. If the objects are many, in this case, mark targets are also many. And if the objects are long-lived, for example, in a server-side application. Okay, demonstration. I want to show the performance improvement with parallel ZC. This demonstration is video game style. Let me explain about this game. Okay. Game title is Super Narihiro ZC. It's a traditional side-scrolling video game. And you should collect the garbage. You should. And C is pop from Z block when you headbutt it. So it's DC. And when you reach the goal, so it's huge display. Exciting. Okay. Then clear. Thank you. And character has hit point. When DC runs, the character loses hit point while waiting for the DC to finish. We must reach the goal before hit point run out. So other characteristics of superNARI DC are this is running in fixed intervals. A lot of objects are generated to increase this burden. Burden level is equals this is game level. Try to compare original DC and parallel DC. Original DC pause time is long. This game will be difficult. But parallel DC pause time is short. This game will be easy. Okay, let's try. Okay. It's original DC version. Okay. So hurry up. Time up because DC pause time is long. So, I mistake. So, good difficulty. Next demonstration is parallel DC version. Okay. It's parallel DC version. Okay. It's very easy. Let's compare average time of DC. In original DC version, this average time is like this. And next, in parallel DC version, like this. And DC count is like this. Okay. I have prepared some additional figures in advance to show you the performance increase in %. So it's faster than the original DC. Okay, finally, I'd like to talk about the remaining problems for parallel DC. Windows OS is not supported. Mac Worker uses pthread as native threads and uses some GCC built-in functions. But I support for Windows eventually. And increased memory usage. Size of one deck is roughly 32 kilobytes. But generally, multiple machines have plenty of memory, so it's okay. Conclusion: I implemented parallel marking DC. DC was improved. I report to RubyConf, but parallel marking has some problems. I fixed these. So you can get source codes here if you are interested. Acknowledgements: the following people helped me make this presentation. I couldn't do this without you. Google Translate. And this is father is gone at last month. I couldn't meet DC without you. Thank you, John. Okay, that's all for my presentation. Gracias.
Thank you for your work, Nari. I had a question. You've been working on the bitmap marking GC. Will this be affected by the parallel marking you're working on?
A little.
A little bit.
A little bit.
Okay. Any timelines? Any idea when you will be able to finish? Or maybe when is next RubyCaigi?
I will propose Ruby's association's grant bitmap marking to implement. So next year you can see bitmap marking, maybe.
Thank you.
Gracias.